In this video, we're going to talk about evaluating limits algebraically. So far in lessons 1 and 2, we've talked about limits in the visual sense. We've looked at a lot of graphs. We've looked at some tables of values. Now we're actually going to look at how do we take a limit given in notation and find an exact answer without a graph. Alright, so by the end of this lesson, you should be able to answer the following little question: how do we evaluate limits algebraically? And as a reminder, by the end of Unit 1, you should be able to answer how do we find the slope of a line using only one point. So let's start with the warm-up. In class, of course, you do this by yourself and we check it, but we'll go through it really quick right now. So the first one, let f of x equal 1 plus the square root of x minus 7. Find f of 16. So what we want to do is just plug in 16 for x. So we'd have f of 16 is equal to 1 plus the square root of 16 minus 7, which is 1 plus the square root of 9, which is 1 plus 3, which is 4. The next one we want to factor completely. 9m cubed minus 63m squared plus 108m. So the first thing we always want to look for when we factor is the greatest common factor. And you might notice here that the greatest common factor is 9m. So if we pull out 9m, we're left with m squared minus 7m plus 12. And we can still factor that trinomial again. So we'll get 9m times m minus 3 times m minus 4. All right, next one says factor completely. A plus 2b quantity squared minus c squared. So you might notice this is a difference of squares, so we can factor it as follows. So our first factor will have a plus 2b minus c. Our second factor will have a plus 2b plus c. And finally, we want to practice rationalizing the denominator of 1 over 2 plus the square root of 3. So to rationalize the denominator, recall that that means we want to get the denominator to not have any square roots. And the way that we do that is we multiply by the conjugate over itself. So that would look like 2 minus root 3 over 2 minus root 3. And then if we FOIL out the numerator and the denominator, we'll get 2 minus root 3 over 4 minus 3, which is 2 minus root 3 over 1, which is just 2 minus root 3. Okay, so that was a really quick review of some algebraic techniques that we're going to use with limits. So now, recall a limit is a y value. Okay, now this may not be an exact y value, but the general idea is we're looking at the approximate y value of a function as x approaches a number. So with this in mind, how might we find the limit of a function like f of x is equal to x squared plus 2x plus 1 over x minus 2 as x approaches 1? Well, if a limit's a y value and we're sort of given an x value, it would kind of make sense to plug in the x value to find the limit. So for example, we could say like f of 1 is 1 squared plus 2 times 1 plus 1 over 1 minus 2, which is 4 over negative 1, which is negative 4. So we could say that this is the limit as x approaches 1 of f of x is equal to negative 4. And we call this method for finding limits direct substitution. Now, we can't do this all the time, but in many nice cases we can. So as long as a function has a y value, we can directly substitute. So how can we summarize this? So when can we use direct substitution? We can use direct substitution when substituting a x value or an x value doesn't cause a domain problem. And what do I mean by a domain problem? Well, that means that we don't get a number over 0 or the square root of a negative number or something bad, okay? So as long as you plug in a number and you get a number as an answer, direct substitution is the way to go. So that was pretty easy, but you know all these problems aren't going to be this easy. So let's start looking at some problems that can happen. So first, what happens if we try to find the limit as x approaches 1 of x squared over 1 over, x squared minus 1 over x minus 1 with direct substitution. So let's go ahead and plug this in and see what happens. So if we try to find f of 1, we would get 1 squared minus 1 over 1 minus 1. Well, this gives me 0 over 0. Okay, so that's a problem because 0 over 0 is undefined or not possible. And so that's kind of what I was talking about up here when we were talking about domain problems. Okay, so this would be a domain problem because we can't divide by 0. So we want to think about how can we use algebra to remove the problem. So the big problem with this is that 0 is in the denominator, and that's happening because 1 minus 1 is 0. So if we can somehow get rid of that x minus 1, so we want to get rid of the x minus 1 in the denominator, causing the problem. So that's kind of the name of the game with limits. So like you find a problem with an easier method, and then you say, okay, how can I use algebra to remove this problem so that I can actually get an answer? Okay, so for example, let's say we have the same limit. The limit as x approaches 1 of x squared minus 1 over x minus 1. So the notes are structured like this, so I'll usually have the example problem written out when we do really long algebraic stuff, and instead with your notes we're going to focus on why we go from each step to the next. So that's kind of what this little chart is for. Okay, so first we always start with our problem statement when we're working an algebraic problem, and so notice that I've rewritten the problem right here, and then I'm going to go into my steps after that. So the first thing I might want to do is I might want to try and just factor the numerator. Okay, so if we notice the numerator is x squared minus 1, which factors as a difference of squares. So this is a difference of squares. And so the reason we can go from the first step to the second step is we can factor the numerator. As a difference of squares. And so why might we want to do this? Well, we notice once we factor it that we get this factor of x minus 1. So that factor of x minus 1 is really nice because it matches the factor of x minus 1 at the bottom. And remember, our goal is to get rid of the x minus 1 in the denominator. So since those factors match, I can now cancel them out, and I'm left with x plus 1. So from the second to the third step, we're canceling the common x plus 1. So cancel common factor, x minus 1. And now we've removed the issue with the original problem. So now, since we're left with just x plus 1, it kind of puts us back into that former example where we did direct substitution, because now I have no denominator, so I can't have a problem with the denominator. So all I have to do now is directly substitute. So that's what this step is. So we direct substituted 1 for x, and we just use some arithmetic and simplification to get our final answer of 2. Okay, so one thing I want you to notice in this is how we showed our work for limits. So if you look at all of these steps together, this is the type of work I'm expecting to see on a test. Okay, so type of work expected. So you should have a problem statement. You should have an equal sign leading you to each step of the simplification. And notice once we substituted for x, we didn't write limit anymore. So limit was not written in these last two steps. Okay, because that's the point where we've actually taken the limit and we're just simplifying from there. Okay, it's going to take some practice doing all of that notation and showing your work in such a structured way, but with practice you should be able to get it. So, enough aside and back to the actual lesson. So we call this method for finding limits factor and simplify. And you're going to notice that this shows up with a lot of examples, so that's why we go ahead and give it a name. So on a graph, this method deals with limits that are holes or removable discontinuities on a graph. So if we were to go back and graph x squared minus 1 over x minus 1, you would notice it's a curve with a hole at the point x is equal to 1. Okay, so let's summarize. When can we factor and simplify? So if we remember, the initial problem, when we tried to directly substitute, gave us 0 over 0. So when direct substitution gives 0 over 0, and both the numerator and the denominator okay, my pen's screwing up here. Okay, numerator and denominator share a common factor. Okay, let's look at another example. So that was one problem that could go wrong. Let's see another problem. So can we factor and simplify the limit as t approaches 0 of the square root of t squared plus 9 minus 3 over t squared? Well, I don't know. How could we factor the top? I don't know, and I don't think that there's a way. So that's kind of the problem here. So if we were to plug in 0, if we were to try direct substitution, we'd have that same issue of 0 over 0 coming out, but now we can't factor. So for this problem, we're going to need to introduce another strategy, which we call rationalizing the numerator. So if you're wondering if this is the same thing as rationalizing the denominator, you are exactly right. This is exactly the same as rationalizing the denominator, except instead of getting the square roots out of the denominator, we want to get them out of the numerator. Okay? And again, that's going to help us cancel the denominator problem, just like we did in factor and simplify. So let's take an example. Let's evaluate the limit as u approaches 2 of the square root of 4u plus 1 minus 3 over u minus 2. So once again, we start with our problem statement. So notice I've rewritten the problem in its entirety. And the first thing we're going to want to do to rationalize the numerator is multiply by the conjugate of the numerator. So multiply by conjugate of numerator, which we sometimes call a well-chosen one because it's a number over itself, which would simplify to 1. And just a reminder, the conjugate means we flip the sign in between the two terms of the numerator. Okay, so notice we had a minus, so we swapped that minus to a plus. Okay. So now that I've multiplied by the conjugate, the next thing I want to do is actually work on simplifying the thing inside of the limit. So that means foiling across the top and across the bottom. However, typically with these, I want to leave the denominator unfoiled because the whole goal is to cancel this u minus 2 eventually. So if I foil it in there, it's going to be a lot harder to spot it at the end when I want to cancel. So what we're going to do is we're just going to FOIL the numerator. And leave denominator factored. So we can cancel at the end. Okay, so that's how we get this step. So notice once we've FOILed, there, and, FOILing all those four things, we should end up with 4u plus 1 minus 9 over u minus 2 times the square root of 4u plus 1 plus 3. Okay, so now I want to continue to simplify the numerator, so I notice I can combine that 1 minus 9 into a minus 8. So that's what I'm going to do in this next step. I'm going to simplify the numerator. Alright, so now that I've simplified the numerator though, I notice so maybe I don't notice, but I remember my goal of wanting to cancel the u minus 2. So now I want to think, how can I force that numerator to have a u minus 2 show up in it? And that's when you might notice, well, if I factor out a 4, or factor out that greatest common factor of 4, I'll end up with a factor of u minus 2 left over. So the next thing we want to do is factor the GCF of the numerator. And so what that means is I'm going to pull out that factor of 4, and I'm going to be left with u minus 2. Okay, so now I have a u minus 2 factor on top, u minus 2 factor on bottom. That's really good. So now I can cancel these two, and I'm left with just 4 on the top and the square root of 4u plus 1 plus 3 on the bottom. So we can summarize this as cancel common u minus 2 in numerator and denominator, or in top and bottom. And now we've removed the problem, or the issue. It gets confusing when you say problem for too many different things. So now we've removed the issue of u minus 2 is equal to 0. Okay, so now that I've removed the issue, now we're all the way back in that case of direct substitution. So now if I try to plug in 2, I'm not going to have an issue. So that's what I'm going to do next. So I'm going to direct substitution. And notice once again, once I substitute that number, I'm not writing limit anymore in my work, because now I've actually taken the limit once I substitute a number. And from here, it's just going to be some arithmetic and simplification. So that's how I'm going to finish up this table. And I get for my final answer 1/3. Okay, so let's summarize. When can we rationalize the numerator? What features in our problem are we looking for? Well, the denominator is, maybe we should say it like this. Direct substitution gives 0 over 0, but factoring is impossible. And there's a square root in the numerator. So that's an important thing with rationalizing. If we don't have a square root, we can't rationalize. Okay. Now, these same strategies actually apply to one-sided limits. So far we've only done regular two-sided limits, but actually they apply to one-sided limits as well. And you'll see this a lot with piecewise functions. So piecewise functions frequently require one-sided limits, and one very common piecewise function is the absolute value function. Now, you've probably seen the absolute value function before, but maybe you only saw its graph and you didn't see the piecewise definition. So the absolute value function, as a refresher, we use the notation x with bars around it to denote absolute value, and this is equal to the piecewise function. So this is what we call the piecewise definition of the absolute value function. It's the function x when x is greater than or equal to 0, and it's negative x when x is less than 0. So as a picture, this looks like a V. So we've got like a line of slope +1 in the first quadrant, and we've got a line of slope -1 in quadrant 2. And so that is f of x equals absolute value of x. Okay, so we're going to use this piecewise definition to help us evaluate limits involving the absolute value function. So first, let's look at the following example. Show that the limit as x approaches 0 of the absolute value of x over x does not exist. Okay, so the way that this work is going to be structured is we're going to say that we're doing a proof. Okay, I don't want that word to scare you. Basically, that just means we're going to show our work, but we're showing that a certain statement is true. So it's not like we're just solving a problem here. The problem actually says show that this limit does not exist. So we're trying to give work to say why that statement is true. Okay, so we will show that the limit does not exist by showing that. So when we write, when we show our work for a proof, usually we start by saying what we're going to do. Okay, so first we're going to show that the limit does not exist by showing that the left-hand limit does not equal the right-hand limit. So remember back to the visual limits. Basically, when a limit did not exist, we said it was because whatever value it approached on the left side was not the same as the right side. So our strategy for this problem is going to actually be to compute the two limits and show that the two numbers are actually not the same. So let's start with the left-hand limit. So I start by writing my problem statement. So notice I've written the limit as x approaches 0 from the left of the absolute value of x over x. Okay, so now here comes the slightly tricky part. Since we're approaching from the left, we want to represent the absolute value with the part that makes sense with the x values we're using. Okay, so let me repeat that. So we're looking at the 0 from the left, so that means we're taking numbers less than 0, and we're trying to find the y value of absolute value of x with those x values. So if we think about our piecewise definition, what does the absolute value of x look like when x is less than 0? Well, it actually looks like negative x. So what I'm going to do is I'm going to use negative x in place of the absolute value because they should be the same thing for the certain x values that we're using. So that's what I've done in this step. So notice, in place of the absolute value of x, I've just substituted negative x. So we can summarize this by saying substitute negative x for absolute value of x, since here we're saying x is less than 0. Okay, and now I have a limit that I can evaluate just like we've been doing in the previous example. So we have to figure out, can we directly substitute? Can we use factoring? Can we use rationalizing the numerator? Now here, this isn't too bad of a limit. We notice first of all that the two x's we can cancel because they're common. So we cancel that common x, and we're left with negative 1. So here, we don't have any more x's, so there's nothing to substitute. So our final answer is just negative 1. So final answer, nothing to substitute. Okay, so the limit as x approaches 0 from the left of the absolute value of x over x is equal to -1. So this is the left-hand limit. Okay, now let's look at the right-hand limit. So we're going to do a similar thing. So if the left was a little confusing, hopefully when we do this very similar right-hand limit, it'll start to make a little more sense. So now I'm going to rewrite my problem statement for the right-hand limit. So I have the limit as x approaches 0 from the right of the absolute value of x over x. And I want to think about the same thing I did with the left. 0 from the right means that my values are greater than 0. Okay? So that tells me that I can represent absolute value of x with just x because x is greater than or equal to 0. So what I'm going to do is in place of absolute value of x, I'm going to sub in just x. And I'm going to summarize that in the table. So we substitute x for absolute value of x since x is greater than 0. Okay, now just like the left-hand limit, those x's are going to cancel because they're the same thing. And we're just left with the limit as x approaches 0 from the right of 1. So we canceled those common x's. And we're left with 1. But now there's nothing to substitute because I don't have any variables of x left, so 1 is my final answer because there's nothing to sub. Okay, so now I've computed my left-hand limit, I've computed my right-hand limit, and now I want to make sure that I answer the initial question. So sometimes with this, it's very easy to get caught up in all this work and not remember the initial question you were supposed to be answering. We're supposed to be showing that the particular limit does not exist. Okay, so we always need to end our work with a conclusion, which is basically a sentence that answers the question. Okay, so conclusion. Since, and I'll erase these little tidbits just so we have room. But since the limit as x approaches 0 from the left of the absolute value of x over x is equal to -1, which is not equal to 1, which is the limit as x approaches 0 from the right of the absolute value of x over x. So what we're saying in this statement here is that we're summarizing the work we just did, and we're saying that those limits are not equal. We can say that the limit overall does not exist. Okay, so there was a lot of notation there, so if that's confusing, make sure you ask some questions, okay? So that's the end of lesson 3. The last thing you need to do is just fill out the check your understanding question here. So make sure to answer the little question, how do we evaluate limits algebraically? All right, that's the end of this video.